Good afternoon, everyone. I'm Wenbo Ding, and I'm a second-year PhD student at Clemson University. I'm working with Dr. Hongxing Hu. Today, I will give a talk about our recent work on the safety of IoT devices' physical interaction controls. As we know, smart home is a very important area in IoT domains. The market size of the smart home is very huge. As you can see, it is expected to reach more than $53 billion in the year 2022. The amount of smart home devices are also growing very fast, and the functions provided by these devices are also getting more and more complicated. Besides, there are also several existing commercial platforms for smart home, such as Google's Home, SmartThings from Samsung, the Apple's HomeKit, and Amazon's Echo. Here is a typical environment for smart home. As you can see, there are many smart devices, such as Wi-Fi lights, the smart thermostats, and like something else like the connected windows and the smart oven. All these devices are connected to a centralized hub in current platforms. And these devices could communicate with each other through traditional wireless network, such as Wi-Fi, Bluetooth, or Zigbee. However, there are also some other interactions between these devices. Since these devices could communicate with each other through the physical environment, they could have an impact on each other through this physical environment. For example, the connected window if you open a window, it might change the illumination in your room, and these changes may trigger the actions of the smart bulbs. And besides, if you open a window, it might also change the temperature in a room, and this might trigger the actions of the thermostat. Other devices such as the oven or toaster, if they have some problems, they may trigger the smoke sensor to give you an alarm. These physical functions of smart home devices are very necessary, and these physical interactions of IoT devices can bring significant convenience to the users, and that's why we use them at our home. But these physical interactions can also be used by attackers, and this is the main motivation of our work. Ideally, devices of these IoT devices are only controlled by applications. By setting the proper applications, the user could manage the behavior of devices in the way they expected. As shown in the graph here, a heater control application would turn on the heater at a specific time. Assuming this application is compromised by some attackers, or basically itself is malicious applications, because the heater could change the temperature in the room, this application could cause some unexpected interactions. And these unexpected interactions could be utilized by the attackers. For example, if the temperature is rising by the heater, and the change of this temperature is detected by a temperature sensor, the temperature sensor could trigger another temperature control application to open the window. And so the attacker could open a window by turning on the heater at the first place, and this might lead to the potential intrusion or breaking problems. To address these problems, we designed a system called IoT Mon, and this system is able to capture all the physical interactions between devices and enable the safe interaction controls on the devices. To achieve these goals, we have three main challenges to solve. The first challenge is that we need to find a method to identify all the physical channels automatically. After identifying all the physical channels, we need to generate all the inter-applications interactions as shown above. And after we have all the interactions chains, we need a method to evaluate the risk level of all these interactions and try to eliminate the risky ones. To solve these challenges, we propose our IoT model structures here. Our system includes three main components: the application analysis, the interaction chain discovery, and the risk analysis and the mitigation. The first module, application analysis, contains two subcomponents. The first is Intra-Application Analysis, and the second is physical channel identification. The first subcomponent aims at extracting the intra-application interactions from the source code, from the applications itself. And the physical channel identification is used to analyze the descriptions of the applications. So we could extract the physical related keywords from the descriptions of applications. The second module takes all the intra-application interactions and physical channel informations as input and combine them together to generate the inter-application interaction chains. The third module provides a risk analysis and mitigation method for all the inter-application interaction chains. It has 4 steps. The first is behavior modeling, and then clustering, then risk evaluation, and in the end, risk mitigation. And I will give more details in the later discussions. The first component is the intra-application analysis. As we said before, this component aims at extracting the intra-application interaction flows from the applications. And this component has 4 steps. Firstly, we use a general model called IFTDT to capture all the necessary informations. And then we use a AST construction to build the AST. And in the third step, we traverse all the input sections to get the capabilities it used. The capabilities is declaration in the system, which means what kind of devices might be used in my applications. And in the last, we tracing all the functions and the variables, so we could build the interactions from the trigger capabilities to the action capabilities. Here is an example of our intra-application analysis. The app provides the function locate when I leave, and first here is this piece of code is checking the status of some present sensor, so the application could know whether there is someone at home or not. And this part is the action of the applications, which will unlock the door or turn on the switch based on the conditions before. And by tracing the application capabilities used at the beginning input sections, we could build this intra-application interaction flows from the present sensor to the locks and the switches. And then another very critical component is a physical channel identification. This component aims to extract the physical channels from the application's descriptions by natural language processing. By using natural language processing, we want to guarantee the coverage of our method to identify all possible physical channels. This physical channel identification contains 4 steps. First is a parser. We use a parser to divide all the sentences into words. And then for this word, we extract the nouns from all the words. We focus on nouns because we found that the nouns could contain all the physical related informations. So we just use them rather than verb or other things for further analysis. The third is that we use walk-to-vector to calculate the similarity between these nouns. And based on the similarities, we can cluster them into different groups. In the end, for different groups, we choose the most representative words to represent this kind of categories, physical information keywords. And there could be some categories may not be physical related, and we will remove them manually. Here we give an example of how we do the physical channel identification. This is step first, we use static analysis to extract all the descriptions from applications, and then we put all the descriptions into a parser to separate them into words, and we extract the nouns from them to do the clustering and summarize the channels. And here is an example from application called If It Moved. So the description says send a text when movement is detected, and we use a parser to separate them into different words, and you can see the movement contains some physical information, but also there are some other words like text, which does not contain such information. And in the end, by combining all the words together, you can see different words will be separated into different categories. And the first category will contain some movement information, and category 2 will contain some temperature-related information. And we choose the most representative word from each categories. And here is a summary of physical channel identification result. We identify 7 physical channels from all the 185 sensor applications. And these channels are temperature, humidity, illumination, motion, location, smoke, and leakage. These are pretty straightforward channels. And we also identify the relationship between the capability and these physical channels, so we can use this information for the further chain generation. The next step is interaction chain generation. The input here is that we combine all the information above, like the intra-application interactions and the channel informations. And the output is the intra-application interaction chains. Here we give a simple example. Here we have 2 intra-app interactions. The first is temperature control interaction, and the second is the switch control interactions. And we already know that the signal state will be connected to the temperature channel, and the temperature sensor is also connected to the temperature channel. So these 2 could be linked through this channel and form these interaction chains. After we have all the interaction chains, we need to know which of them are risky and which of them are not risky. So we build the risk analysis module. In this module, first we need to know, since we need to know which of the interactions are risky, we need to set up the baseline. So we use intra-application interactions as a baseline because these interactions are developed by Samsung's developer, and we think these interactions can be trusted. So we use a modeling method to map them into a baseline vectors. For the inter-app interactions, we also use the same method to model them and compare them with the baselines. This process is called risk calculation. If the inter-app interactions vectors is similar to the baselines, we will think them as non-risky interactions. Otherwise, we will treat them as risky interactions. And now we are going to introduce our method for how to set up the baselines. The baseline settings has two steps. The first is a distance-based behavior modeling method. In this method, we give different channels a well-designed value, so we can change the interactions into quantified vectors. And the second step is a distance-based clustering method, such as k-means. By using the clustering, we could group all the trusted interactions into different groups, and these groups will be considered as a baseline. So how we model, in this step, the modeling is very critical, and how we modeling these behaviors we will give it here. To translate the flows to translate the interaction flows into the vectors, the modeling method contains three steps. The first is channel correlation discoveries. In these steps, we try to identify the channel correlations between the interactions. Like, for example, if the two of the channels appeared a lot together in the applications, then we will consider them as are very close related and has high correlations. If then, based on the correlations, we give different channels different values. If they have a very strong correlation, we give them very close values, and then we can map this kind of interactions into the vectors. And after the modeling, we can cluster them into baselines and also do the risk calculations. Here is a clustering method. For example, we have different intra-application interactions, and we cluster them into two different categories. The first is temperature related, and the second is motion related. And two of the temperature-related interactions could also form an interaction chains here, and we also map them into the vector space. If this vector fall into any of the baselines, we will consider them as non-risky. If not, the distance between it and the closed baselines will be used as risky scores. This risky scores just implies how similar it is to the existing baselines. And for the for those risky interactions, we need to eliminate their risks. So we propose different methods for different users. For developers who can change the applications, we suggest that they could add some new trigger conditions. For example, here we could add a location sensor checking to the window control applications. So someone must be at home before the application could turn on your windows. And here is an example how we add the new conditions into existing applications. For the normal user who cannot change the applications, we just give them warnings, and they could probably change their settings or remove some applications. Next, we discuss our evaluation result. Here is a data set of our evaluation. We use all the applications from Samsung's official platforms. And the data set we use for natural language processing for similarity calculation is a Google News data set. And the devices we have are common smart home devices such as sensors, locks, switches, and so on. For the intra-app analysis, we succeed in analysis 135 applications. The 50 of them are not analyzed because some of them are device drivers who does not contain any information about interactions, and some of them just just use too many capabilities and didn't give predefined interactions. And here we give an example that how we identify the triggers and the actions of the applications. Next, besides the summary we provided above, we also identify the capabilities between and the channel relationships. So that's how we map the channels and the capabilities to the connected interaction chains. And after we have all this information, we generate 162 interactions between applications, and 37 of them are risky interactions. To prove the effectiveness of our modeling and risk analysis, we compare our result with randomized initialization method. In this random method, we just give the channels random values. So when we model them, they will be mapped into some other vectors. And you can see our method could identify the correlation between channels more effectively. And our method has a much higher positive rate for identify risky interactions. And here is a summary of our interaction, all the interactions among these applications. And if we zoom in, the red dot means it's a channel, and the blue dot means this is some capabilities provided by the applications. And the red lines means this is the risky interactions. If we zoom in, we can see that this is the example of risky interactions. And you can see the temperature rising will causing the home mode to be changed. And the home mode, if it changed, it could trigger some switches to be turned on or turned off. And here we also give the top 10 risky interactions. I just introduced number 5 here. And the first one is interaction from the home mode to the log. So in this interaction, if someone go back home and some switches is triggered, for example, a heater or a toaster is connected to such switches, it might trigger the smokes and trigger the door to unlock. And the second one is that the timer could trigger the motions of some devices, and these devices could trigger the changes of the home mode. The performance of our system is very linear, like with growing of our applications, the time is just growing very linear. And here is the conclusion that our system could identify 7 physical channels and identify 162 potential chains. 7 of them are risky interactions. And for the future work, we might do some new attacks or do some more fine-grained mitigation solutions. Yeah, that's all. Thank you.
So we do have time for 1 or 2 questions.
If nobody else wants to ask, I will. Thank you very much for the talk. I'm not sure it's more of a question or a comment. A lot of what you were presenting reminded me of work that was done around feature interactions in telecommunication systems. And I'm wondering, are we seeing emergence of a similar kind of problem? And how does this relate to all this kind of body of work that has gone on, for a long time around feature interactions in telecoms, where the similar kind of dynamicity applies?
Sorry, can you repeat it? Because
so there is a body of work around feature interactions in telecommunication systems, which is exactly the same kind of problem, where you have multiple features that dynamically compose, and then you may have pathways which you do not want to allow.
Yeah.
And my question was, is this quite similar, or what's distinct in terms of the problem that you're trying to solve?
Okay, so first thing is that I'm not quite familiar with the area you mentioned before. So, and this work is just basically focused on the physical interactions between like smart things, smart home devices. And I think the suggestion you gave might be useful.
It might be good because there are parallels. I don't know if there is something very different here or not, but there are definitely parallels. Yeah. And it may be that the IoT provides more complex scenarios than telecom systems. Yeah. But I think it may be well worth looking into that.
Yeah. Thank you. Thank you for the suggestion.
So just a clarification. If you just look at the policy, you will find that, for example, the temperature will be increased because of this. And you find another rule that you will say the window will be opened because of the temperature. Don't you think you can do this analysis only by looking at the policies of each one of these apps and see the correlation between these features and understand that if there is interdependency, and then you can do something about it? Do you have to do that static analysis and so on?
Yeah, we have think about this problem because we want to do a static analysis to generate all the interaction chains. But one thing occurs is that in this system, there are so many capabilities that can be used, and the physical influence of these capabilities is not clearly defined. So first, for example, some capabilities could have the same physical influences, and some channels could also have an impact on multiple capabilities. So we just so how to group them together, like different capabilities with the same physical features, how to group them together is what we try to do here. So that's why we use the natural language processing first to summarize them together and summarize all related capabilities into the same physical channels. So that's why we use the natural language processing here.
But so the relationship between humidity and temperature is not going to be found in the description. This is a physical thingy that's been described in differential equations of how humidity affects temperature.
Yes, that's the correlation between channels.
Yeah,
so that's a problem we have, and we try to solve them in the future, maybe like some runtime monitoring or some other mechanism to try to identify this kind of correlations. Yes. Thank you for the question.
Okay, if there's no further question, let's thank the speaker again.